What if we're not alone? For centuries, that question has haunted astronomers and dreamers alike, sparking debates, fueling conspiracy theories, and inspiring countless stories. But here's something even more fascinating. Every year, as our telescopes peer deeper into space, we uncover worlds that defy our wildest imaginations. Planets shrouded in eternal twilight, moons with hidden oceans, even entire star systems that could rewrite the rules of biology as we know them. The universe isn't just vast, it's teeming with possibilities, and the evidence is mounting that life might be hiding in plain sight. Think about it like this: searching for alien life is like looking for needles in a cosmic haystack, except the haystack is unimaginably enormous, and we've only just begun to understand where the needles might be hiding. From the infamous Fermi Paradox, which asks why we haven't found extraterrestrials yet, to jaw-dropping UFO sightings that still baffle scientists, the clues are everywhere. But here's the twist: we no longer have to rely on speculation alone. Cutting-edge technology is finally giving us the tools to explore these mysteries in ways we once thought impossible. That's where this journey begins. Today, we're diving into 25 of the most mind-bending cosmic wonders, places where alien life could already exist, waiting to be discovered. Whether it's the icy geysers of Europa, the methane lakes of Titan, or the bizarre megastructures orbiting distant stars, each of these locations holds secrets that could change everything. So buckle up, because we're about to explore corners of the universe where reality might just be stranger than fiction, and where the answer to humanity's oldest question could finally be within reach. Hidden beneath a frozen crust of ice, stretching farther than all of Earth's oceans combined, lies one of the most tantalizing mysteries in our solar system: Jupiter's moon, Europa. This isn't just another icy rock drifting through space. Europa is a world where the very conditions for life might be brewing right now, sealed under miles of cracked and shifting ice. Picture an alien ocean, dark and vast, warmed not by sunlight but by the relentless gravitational tug of war between Europa and its monstrous parent planet, Jupiter. Every time Europa orbits, Jupiter's crushing gravity squeezes and flexes the moon's core, generating enough heat to keep that subsurface ocean liquid and possibly habitable. Sound familiar? It should. On Earth, life thrives in the most unexpected places, including scalding hydrothermal vents at the bottom of our oceans where sunlight never reaches. These vents spew mineral-rich plumes, fueling entire ecosystems of bizarre creatures. Now imagine Europa's hidden sea with its own version of these vents, powered by the moon's churning core. Could alien microbes, or something even more complex, be thriving there? The clues are stacking up. Hubble Space Telescope observations have spotted what appear to be plumes of water vapor erupting from Europa's surface, hinting that its ocean might be venting into space, offering us a free sample if we're clever enough to catch it. That's exactly what NASA Europa Clipper mission aims to do. Slated to launch in the coming years, this spacecraft won't land on Europa's frozen surface, but it will swoop in close, skimming just 25 kilometers above its terrain. Armed with a suite of cutting-edge instruments, Clipper will analyze those mysterious plumes, map the thickness of the ice shell, and even measure the depth and salinity of the ocean below. Scientists are practically giddy with anticipation, because if Europa's ocean holds even the simplest forms of life, it would prove that Earth isn't the only oasis in the cosmos. But here's the real mind-blower: Europa may not be alone. Its sister moons, Ganymede and Callisto, likely harbor their own subsurface oceans, making Jupiter's neighborhood a prime hunting ground for alien life. The implications are staggering. If life can emerge in the dark, pressured depths of a moon light years away, what else might be out there waiting in the frozen shadows of the universe? Europa is just the beginning, and with every mission, every discovery, we're peeling back the ice to reveal answers that could redefine our place in the cosmos. While Europa's frozen mysteries captivate our imaginations, Saturn's moon Enceladus might just one-up it with one of the most spectacular shows in the solar system: massive geysers, erupting from cracks in its icy shell, shooting water hundreds of kilometers into space. Imagine a world so active, so vibrant, that it quite literally spits its secrets into the void for us to study. That's Enceladus, a small, unassuming moon, barely 300 miles wide, yet packing enough intrigue to rival planets 10 times its size. The real game-changer came when NASA Cassini spacecraft swooped through these towering plumes, analyzing their contents in a series of daring flybys. What it found was nothing short of revolutionary. Not just water vapor, but organic molecules, the building blocks of life, mixed with salts and silica particles. These weren't just random compounds. Their chemistry pointed straight to hydrothermal activity on the ocean floor, where hot water reacts with rock, creating the kind of energy-rich environment that on Earth fosters thriving ecosystems. It's as if Enceladus handed us a cosmic business card with its address scribbled in chemistry. Dig deeper and the picture gets even more compelling. Unlike Europa, where the ocean is locked under miles of ice, Enceladus practically invites us in. Those geysers offer a direct pipeline to the hidden sea below, meaning we don't need to drill through the ice. Nature's already done the hard work. Scientists believe this subsurface ocean is global, wrapped around the entire moon, and likely kept warm by Saturn's gravitational kneading, much like Jupiter does to Europa. But here's the kicker: the water is salty, with a pH level eerily similar to Earth's oceans. If life ever needed a recipe to get started, Enceladus seems to have all the ingredients: water, energy, and chemistry simmering in its depths. And let's talk about those geysers for a second. Their sheer power suggests this isn't some sluggish, barely there process. Enceladus is dynamic, pumping out material with enough force to create one of Saturn's faint outer rings. This isn't just a trickle, it's a declaration, a sign that something profound is stirring beneath the ice. Could microbial life be hitching a ride on these jets, flung into space like interstellar confetti? It's not out of the question. Future missions like the proposed Enceladus Orbiter aim to find out, potentially carrying instruments designed to sniff out amino acids or even simple cellular structures in the plumes. But here's the twist that makes Enceladus truly special: accessibility. While Europa's ocean might be richer, it's buried under daunting ice layers. Enceladus, by contrast, wears its heart on its sleeve, or rather in its plumes. Sampling them could be the fastest route to answering whether life exists beyond Earth. And with private ventures now eyeing missions to Saturn's moons, we might not have to wait decades for answers. Enceladus isn't just a candidate for alien life. It's a front-row seat to one of the greatest discoveries humanity could ever make. So while Europa gets the headlines, don't sleep on this icy underdog. Enceladus is proof that sometimes the most extraordinary things come in the smallest packages, and that the universe has a way of putting its secrets right where we can reach them. Mars, our rusty next-door neighbor, has teased us with possibilities for generations. What was once the subject of wild tales about canals and alien civilizations is now one of the most intensely scrutinized worlds in the solar system. And for good reason. Beneath its barren, windswept surface, Mars might still hold the echoes of life, or even whispers of something still alive today. Let's start with the obvious: water. Orbiting spacecraft have mapped dried-up river valleys, lake beds, and even ancient shorelines, painting a picture of a world that once looked strikingly like Earth. Billions of years ago, Mars had rain, rivers, and possibly vast oceans. And where there's water, there's potential for life. But here's where it gets even more intriguing. Those ancient waters might not be entirely gone. In 2018, scientists using ground-penetrating radar discovered what appears to be a massive subsurface lake near the Martian South Pole, buried under a mile of ice. And if there's one thing we've learned from places like Europa and Enceladus, it's that where there's liquid water, life might just find a way. That's exactly what NASA Perseverance rover is hunting for right now in Jezero Crater, a site that was once a river delta where water once carried sediments rich with organic material. Perseverance isn't just looking for fossils, it's collecting samples that could one day be returned to Earth, potentially holding the first definitive proof of extraterrestrial life. But Mars hasn't made it easy. The planet serves up tantalizing clues like mysterious bursts of methane in its atmosphere. On Earth, methane is often produced by living organisms, and while geologic processes can also release it, the sporadic nature of these Martian spikes keeps scientists guessing. Could microbes deep underground be the source? Then there's the controversy. Back in the 1970s, the Viking landers conducted experiments designed to detect life. Some results seemed positive, a chemical reaction that looked like metabolism. But without organic molecules clearly identified in the soil, the findings were dismissed as a fluke. Decades later, some researchers still argue Viking might have found something after all. And let's not forget the infamous Martian meteorite LH84001, a rock blasted from Mars that, in 1996, scientists claimed contained microscopic structures resembling fossilized bacteria. The debate raged for years, with critics dismissing the shapes as natural mineral formations. So where does this leave us? Mars is a world of contradictions, bone dry on the surface, possibly wet below, littered with clues but stubbornly secretive. If life ever existed there, it might still be clinging on in underground aquifers or buried deep in the soil. Or perhaps it flourished billions of years ago, leaving only fossilized traces behind. Either way, Mars isn't done surprising us. With new missions on the horizon, including human expeditions, we may finally get the answers we've been chasing for centuries. And if we do, it could rewrite not just our understanding of Mars, but our place in the cosmos. If Europa and Enceladus are water worlds hiding beneath their icy shells, Saturn's largest moon, Titan, is something far stranger, a looking-glass version of Earth where the rules of chemistry twist into alien shapes. Picture a landscape eerily familiar yet utterly alien. Rivers carving valleys, waves lapping at shorelines, even rain falling from hazy orange skies. But these aren't made of water. On Titan, liquid methane and ethane take center stage, flowing across the surface in a slow-motion dance of hydrocarbons. This isn't just another moon, it's a laboratory for life as we don't know it. What makes Titan so compelling isn't just its Earth-like geography, it's the tantalizing possibility that life could exist there, built on a completely different blueprint. On Earth, water is the universal solvent, the essential ingredient for biology. But Titan's bitter cold, dipping to -180 degrees Celsius, turns water into rock-hard ice. Instead, liquid methane fills the role, pooling in vast lakes like Ontario Lacus, a methane sea larger than North America's Lake Ontario. Could life adapt to such extremes? Some scientists think so. Hypothetical methane-based organisms, dubbed azotosomes, might use hydrocarbon chains instead of cell membranes, relying on chemical reactions we've barely begun to imagine. Then there's the atmosphere, thick, nitrogen-rich, and swirling with organic compounds. When sunlight hits Titan's upper layers, it triggers reactions that create complex molecules like acetylene and hydrogen cyanide. These compounds rain down onto the surface, coating dunes and riverbeds in a sticky probiotic sludge. It's like the primordial soup of early Earth, but frozen in time and drenched in methane. The sheer abundance of organic material has led some researchers to wonder, if life emerged here, would we even recognize it? Enter Dragonfly, NASA's audacious plan to send a nuclear-powered drone buzzing across Titan's dunes by the mid-2030s. This isn't your typical rover. Dragonfly will hop from site to site like a mechanical insect, sampling the surface and sniffing the air for signs of chemistry gone wild. It targets those organic, rich regions where the building blocks of life, however alien, might be assembling themselves into something more. Imagine a machine skimming over hydrocarbon lakes, dodging methane raindrops, hunting for clues in a world where every drop of liquid is a potential puzzle piece. But here's the kicker: Titan's mysteries don't stop at the surface. Buried beneath its icy crust, there's strong evidence of a subsurface ocean, one that might mingle with the methane above through cryovolcanoes or fractures. That means Titan could harbor two potential havens for life, one in its bizarre surface chemistry, another in hidden waters like Europa's. Talk about hedging your cosmic bets. So while Titan might lack the immediate drama of erupting geysers or rusty Martian valleys, it offers something perhaps even more profound: a chance to rewrite the playbook on what life is. Whether it's methane-breathing microbes or some yet undreamt form of biology, this hazy orange moon is a reminder that the universe doesn't play by our rules. And with Dragonfly on the horizon, we might soon find out just how creative nature can be when handed a completely different set of ingredients. Venus might seem like the last place to search for life, a scorching, toxic world with surface temperatures hot enough to melt lead and atmospheric pressures that crush submarines. But look higher, about 50 kilometers above that inferno, and the story takes a bizarre twist. Here, in the planet's upper cloud decks, the environment becomes almost hospitable. Temperatures hover around 30 degrees Celsius, balmy by Earth standards, and the pressure drops to something resembling our own atmosphere. It's as if Venus tucked away a secret oasis in its skies, a layer where, against all odds, life might just find a foothold. The real shocker came in 2020, when astronomers announced they detected phosphine in Venus's clouds. On Earth, this stinky, flammable gas is almost exclusively produced by living organisms, microbes thriving in oxygen-free environments like swamps and animal guts. Finding it on Venus was like stumbling upon a smoke signal in a desert. The scientific community erupted. Could this be evidence of floating microbes drifting in the sulfuric acid clouds? The debate raged, with skeptics pointing out that phosphine might form through unknown geological processes. But the possibility lingered, fueled by Earth's own extremophiles, microbes that thrive in acidic hot springs or toxic mine drainage, proving life can adapt to the harshest niches. Here's the catch: Venus's clouds aren't just mildly acidic. They're essentially showers of concentrated sulfuric acid, a substance that dissolves metals and obliterates most organic molecules. Any hypothetical Venusian microbes would need biochemistry unlike anything we've seen, perhaps with protective coatings akin to microscopic armor, or enzymes that harness sulfuric acid for energy. Even water, the universal solvent for life as we know it, is nearly absent. But nature loves a challenge. Some scientists speculate that if life exists there, it might use sulfuric acid droplets as tiny bioreactors, recycling sulfur compounds in a self-sustaining loop. The wild card: those clouds aren't static. Venus's upper atmosphere hosts mysterious dark patches, streaks that absorb ultraviolet light, shifting and changing over time. Some researchers suggest these could be vast colonies of sulfur-eating microbes, a cosmic version of algal blooms. Others counter that the patches might just be exotic chemistry, like iron chloride or crystalline sulfur. Without a dedicated mission, we're left guessing. That's where upcoming projects like NASA Da Vinci and Veritas come in. Da Vinci will plunge through Venus's atmosphere, sniffing for phosphine and other biomarkers, while Veritas maps the planet's surface and weather patterns in unprecedented detail. Together, they could finally crack the case. If life is clinging to those acid-laced clouds, it would rewrite the rules of biology, proving that even in the most hostile corners of the cosmos, nature finds a way. Venus reminds us that sometimes the most unlikely places hold the greatest surprises, floating right where we least expect them. TRAPPIST-1 is the kind of star system that makes astronomers do a double take. Nestled 40 light-years away, this ultra-cool dwarf star barely larger than Jupiter hosts not one or two, but 7 Earth-sized planets, packed so tightly their orbits could fit inside Mercury's. 3 of these worlds sit squarely in the habitable zone, where temperatures might allow liquid water to pool on their surfaces. It's like finding a cosmic Russian nesting doll with potential Earth twins stacked one after another. But here's where things get really interesting. These planets aren't just close to their star, they're likely tidally locked, meaning one side forever faces the light while the other drowns in eternal night. Picture a world where the sun never moves in the sky. On the day side, scorching temperatures could bake the surface, while the night side plunges into icy darkness. Sounds inhospitable, right? Not necessarily. If these worlds have thick atmospheres, something the James Webb Space Telescope is actively investigating, winds could redistribute heat, creating a twilight belt of temperate conditions where life might find refuge. Think of it like Earth's ocean currents, but on a planetary scale, with air instead of water smoothing out the extremes. That's where JWST comes in. This powerhouse observatory has already begun analyzing TRAPPIST-1 planets as they transit their star, searching for the chemical fingerprints of atmospheres. The Holy Grail, detecting gases like oxygen, methane, or even industrial pollutants, hints that something or someone might be altering the air, but there's a catch. Dwarf stars like TRAPPIST-1 are prone to violent flares which could strip away atmospheres over time. The question isn't just whether these planets have air, it's whether they can keep it long enough for life to take hold. Yet the system's compact layout offers a tantalizing possibility. If one planet loses its atmosphere, its neighbors might still cling to theirs. It's a celestial game of survival, with each world writing its own story. And with 3 shots at habitability in a single system, the odds feel almost generous. TRAPPIST-1 isn't just a curiosity, it's a testbed for how common Earth-like conditions might really be. Every flicker of light, every spectral line captured by JWST brings us closer to answering whether we're alone or just late to a cosmic party already in full swing. Just 4 light-years from Earth, cosmically speaking, right in our backyard orbits a world that could rewrite the story of life beyond our solar system. Proxima Centauri b, hugging its faint red dwarf star so tightly that a full year lasts just 11 Earth days, is the closest known exoplanet to us, but proximity isn't its only selling point. This rocky world, roughly 1.3 times Earth's mass, sits in the habitable zone where temperatures might allow liquid water to pool on its surface. The catch: Proxima Centauri isn't your friendly neighborhood star. It's a tempestuous red dwarf prone to violent flares that can unleash 1,000 times the radiation of our sun in mere minutes. Imagine living under a sky where the sun doesn't just rise, it erupts. Proxima Centauri b's star has been caught blasting its planet with X-ray flares so intense they could strip atmospheres and sterilize surfaces. Yet here's the twist: life on Earth thrives in the most unexpected places, from radioactive reactor cores to deep-sea vents. If Proxima b has a robust magnetic field or a thick atmosphere, it might just shield itself enough for hardy organisms to persist. Some scientists even speculate that frequent flares could spark chemical reactions in the atmosphere, inadvertently creating the building blocks of life. Then there's the tidal locking problem. Like many planets orbiting red dwarfs, Proxima b likely has one side permanently baked in daylight, while the other half freezes in eternal night. That sounds like a recipe for disaster unless atmospheric currents or vast oceans redistribute heat, creating a twilight band of survivable conditions along the Terminator line. Think of it as a planetary tightrope walk where life clings to the narrow balance between fire and ice, but the real excitement lies in what we don't know. Proxima b's existence was confirmed in 2016, and since then, astronomers have raced to study it. The James Webb Space Telescope could soon analyze its atmosphere if it has one searching for telltale gases like oxygen or methane. Even more daring are projects like Breakthrough Starshot, which aims to send tiny, laser-propelled probes to the Proxima system within decades. Picture this: spacecraft no larger than a smartphone, zipping past at 20% the speed of light, snapping close-ups of an alien world within our lifetime. Proxima Centauri b isn't just a scientific curiosity, it's a test case for whether life can persist in the chaos of a red dwarf's fury. If this battered world, lashed by flares and locked in a gravitational embrace, somehow harbors life, it would suggest the universe is far more tenacious and far more crowded than we ever imagined. And with each new observation, we're peeling back the layers of a mystery that's literally closer to home than any other. Far beyond our solar system, floating in the dim glow of a red dwarf, Kepler 186f paints a picture of exotic familiarity. The first Earth-sized planet we've ever found lounging comfortably in another star's habitable zone. This isn't just another exoplanet lost in the cosmic census. Imagine standing on its surface, gazing up at a pink-tinged sky, bathed in the perpetual sunset hues of its faint star. Kepler 186f's sun, Kepler 186, is cooler and redder than our own, casting just enough warmth to possibly allow liquid water. But with a catch: the light that reaches this world is a mere fraction of what Earth receives, drenching everything in a dim, muted glow. Now here's the puzzle: could life thrive under such alien sunlight? On Earth, photosynthesis depends on the full spectrum of our sun's rays, with plants greedily soaking up blue and red wavelengths to fuel their growth. But on Kepler 186f, the dimmer, redder light might force life to adapt in radical ways. Hypothetical organisms could evolve to absorb infrared radiation, turning the very weakness of their star into an advantage. Picture forests of black or deep purple vegetation, their leaves optimized to catch every precious photon from their crimson sun. Or perhaps life wouldn't rely on sunlight at all, drawing energy from chemical vents or geothermal heat as it does in Earth's darkest depths. But the challenges don't end there. Red dwarfs like Kepler 186 are notorious for their tantrums flares that can suddenly bombard nearby planets with lethal radiation. Without a robust atmosphere or magnetic field, Kepler 186f's surface could be a harsh place, stripped bare by repeated stellar outbursts. Yet, if the planet has kept a protective blanket of air, or if life has retreated underground or underwater, it might still cling on. The mere fact that Kepler 186f exists where it does raises a tantalizing question. Is this what most habitable worlds look like? Red dwarfs make up over 70% of the stars in our galaxy, far outnumbering sun-like stars. If life can find a way here, the universe might be teeming with it. Kepler 186f isn't just a scientific curiosity, it's a glimpse into the rule, not the exception. A world that challenges our Earth-centric assumptions about where and how life can survive. And as we discover more planets like it, each one pushes us to rethink the boundaries of biology itself. After all, if life can adapt to a world bathed in eternal twilight, what can't it endure? LHS 1140b doesn't just orbit its star, it defies expectations. This super-Earth, nearly 7 times the mass of our own planet, sits snugly in the habitable zone of a small, cool red dwarf about 40 light-years away. But here's what makes it stand out. While many worlds around these temperamental stars get blasted by radiation, LHS 1140b might have a secret weapon, an atmosphere thick enough to shield any potential life from its star's worst tantrums. Think about the odds. Red dwarfs are notorious for their flare activity, often showering nearby planets with enough X-rays to strip away atmospheres over time. But LHS 1140b star is unusually calm for its kind, offering a rare stable environment. Combine that with the planet's likely dense atmosphere, possibly rich in nitrogen or even water vapor, and you've got a world that could hold onto its air for billions of years. That's like finding a diamond in a cosmic storm, a place where conditions might just stay Goldilocks perfect long enough for life to emerge. Then there's the planet itself. Scientists suspect it's a mega-Earth, a rocky giant with enough gravity to cling to a substantial atmosphere, yet not so massive that it turns into a Neptune-like gas ball. Early observations hint at a composition similar to Earth's, with a possible iron core and silicate mantle except scaled up. Picture towering mountain ranges, deep valleys, and vast plains, all under an orange-tinged sky. If water exists there, it could pool in sprawling shallow seas, protected from evaporation by that dense atmospheric blanket. But the real excitement lies in what comes next. The James Webb Space Telescope has already set its sights on LHS 1140b, probing its atmosphere for biosignatures like oxygen, methane, or even industrial pollutants. These observations could reveal whether the planet is a sterile rock or a humming biosphere, and because its star is so dim, contrasts between the planet's atmosphere and the dark backdrop of space are sharper, making it easier to decode the chemical fingerprints hidden in the light that filters through. What if we find something? A thick atmosphere with traces of gases linked to life would catapult LHS 1140b to the top of the astrobiological hit list. It's a reminder that sometimes the most promising worlds aren't the ones that look like Earth, they're the ones that rewrite the rules entirely. In the quiet glow of a gentle red dwarf, this super-Earth might just be waiting to teach us how varied and how resilient life can truly be. GJ1214b isn't just another exoplanet, it's a cosmic enigma wrapped in steam. Located 40 light-years from Earth, this mysterious world is larger than our own but far lighter, as if someone inflated a rocky planet with helium. That's because GJ1214b isn't made of rock and metal alone. Scientists believe it could be a true water world, cloaked in a thick, hydrogen-rich atmosphere, hiding a global ocean so deep it might not even have a seafloor. Picture an endless abyss where the pressure builds to thousands of times what you'd find at the bottom of Earth's Mariana Trench, and the water is so compressed it forms exotic states of ice, not cold but hot, a surreal substance known as supersonic ice. Under that crushing weight, life would face challenges unlike anything on Earth. Yet we know from our own oceans that biology thrives in the unlikeliest places. Take the deep sea vents along Earth's mid-ocean ridges, where scalding, mineral-rich water fuels entire ecosystems of tube worms, blind shrimp, and microbes that metabolize sulfur instead of oxygen. Now imagine GJ1214b's ocean, where the sheer pressure might prevent water from boiling even at scorching temperatures. Could organisms evolve to harness chemical energy from hydrothermal vents buried beneath miles of pressurized liquid? Or would life take an even stranger path, adapting to use the hydrogen-rich atmosphere as a sort of blanket, trapping heat and nutrients in a perpetual cycle? The planet's atmosphere adds another layer of intrigue. Unlike Earth's airy mix of nitrogen and oxygen, GJ1214b's skies are likely a hazy shroud of hydrogen and water vapor, so dense it acts more like a fluid than a gas. Sunlight filtering through this stifling blanket would paint the surface in a dim, reddish glow. If there is a surface, some models suggest the ocean might extend all the way down to the planet's core with no land in sight. But here's the twist. GJ1214b's extreme conditions might not be a death sentence for life. On Earth, we've found microbes called piezophiles that thrive under immense pressure, their cellular structures reinforced with specialized proteins. If similar organisms exist in this exoplanet's depths, they could form the base of an entire food chain, supporting larger creatures adapted to the darkness. Picture gelatinous drifters with bioluminescent lures or pressure-resistant filter feeders sifting nutrients from the slow currents. The real test will come when next-generation telescopes like the James Webb Space Telescope turn their gaze toward GJ1214b. By analyzing starlight filtering through its atmosphere, we might detect chemical signatures, not just water vapor, but perhaps even hints of organic molecules. It's a long shot, but if there's one thing the universe has taught us, it's that life is relentless. From frozen moons to acidic clouds, it finds a way. And if something is stirring in the abyss of this steamy water world, it could redefine not just where we look for aliens, but what we imagine them to be. K2-18b might just be the Goldilocks world we've been waiting for, except it's nothing like Earth. This distant exoplanet, orbiting a dim red dwarf star 110 light-years away, made headlines when astronomers detected water vapor swirling in its atmosphere. Not just traces, but significant amounts, painting the picture of a world where vast, steamy oceans could stretch beneath a thick, hydrogen-rich sky. But here's the twist: K2-18b isn't a rocky planet like ours. It's something far stranger, a potential hycean world, a term scientists coined for planets with hydrogen atmospheres and global water layers, where the very rules of habitability might get rewritten. Imagine a planet where the air isn't nitrogen and oxygen, but hydrogen lighter than helium, clinging to the world in a dense, warm shroud. Under that blanket, the surface could be an endless ocean, not of gentle waves, but of churning, superheated water kept liquid by crushing atmospheric pressure. It's a scenario that defies Earth-based intuition, yet the math suggests such worlds could be prime real estate for life. Hycean planets might actually outperform Earth when it comes to habitability, with their global oceans offering more uniform temperatures and hydrogen atmospheres acting like cosmic greenhouses, trapping just enough heat to keep water liquid even far from their stars. But there's a razor-thin line between a Hycean paradise and a runaway greenhouse nightmare. Tilt the balance slightly, say, if K2-18b's star flares too often, or if its atmosphere thickens beyond a critical point, and that same water vapor becomes a death sentence. Too much heat trapping, and the oceans boil into a steam bath, turning the planet into a pressurized hellscape closer to Venus than Earth. That's the gamble with red dwarf systems. Their habitable zones are so close to the star that planets like K2-18b risk getting bombarded by radiation or locked into irreversible climate spirals. Yet K2-18b holds its secrets close. Initial observations by the Hubble Space Telescope revealed that tantalizing water vapor, but also something puzzling: a shortage of ammonia. In a hydrogen-rich atmosphere, ammonia should be plentiful unless something's actively removing it. Could that something be life on Earth? Microbes devour ammonia as part of their metabolic processes. It's a stretch, but not impossible. Then there's the dimethyl sulfide detected in later studies, a gas that, on our planet, is produced almost exclusively by marine phytoplankton. The data's still controversial, but the implications are staggering. We might be sniffing the air of a world where alien biology is already altering the atmosphere. The James Webb Space Telescope is now turning its golden eye toward K2-18b, and what it finds could redefine our search for life. If this Hycean world harbors even simple organisms, it would prove that life doesn't need Earth-like conditions, just a stable ocean, a few key chemicals, and time. And with red dwarfs making up 75% of the galaxy's stars, Hycean planets could outnumber rocky ones by the billions. K2-18b isn't just a curiosity. It's a glimpse into a whole new class of habitable worlds, ones where the oceans are deeper, the skies stranger, and the possibilities limitless. Deep in the heart of our Milky Way lies a cosmic powerhouse so intense it defies imagination, the galactic center. This isn't just another region of space, it's a swirling maelstrom of stars, gas, and one of the most enigmatic objects in the universe, Sagittarius A, the supermassive black hole anchoring our entire galaxy. Surrounding it, packed tighter than sand on a beach, are billions of stars, many of them ancient red giants, blazing blue supergiants, and elusive neutron stars. But here's the twist: where there are stars, there are usually planets. And in this stellar metropolis, the possibilities for alien life take on a scale as vast as the environment itself. Consider the sheer density of this region. Within just a few light years of Sagittarius A, stars orbit at breakneck speeds, some completing full revolutions in mere decades. Amid this chaos, any planets would be bathed in relentless radiation and gravitational tides. Sounds hostile, right? Yet life on Earth has proven it can thrive in extreme environments, from deep sea vents to radioactive waste. Now picture a civilization advanced enough to not just survive here, but to harness the energy of their surroundings. The concept isn't pure science fiction. Theoretical physicists have long speculated about Type 3 civilizations on the Kardashev scale, those capable of utilizing the energy output of an entire galaxy. And what better place to look for such a civilization than the energy-rich core of the Milky Way? Black holes, ironically, might be the ultimate power plants. The accretion disks around supermassive black holes like Sagittarius emit staggering amounts of energy as matter spirals inward. A sufficiently advanced species could, in theory, tap into this process using technologies we can barely conceptualize, like Dyson spheres built around the event horizon or magnetic fields channeling jets of plasma. Even more intriguing are the orbits near a black hole's innermost stable limit, where time dilation effects could make relativistic computing or communication feasible across vast distances. But let's not forget the stars themselves. In such a crowded neighborhood, planets could exchange material or even life through panspermia carried by asteroid impacts or stellar ejecta. Intelligent species might communicate via tightly focused lasers or gravity waves, signals easily lost in the background noise unless you know where to look. And then there's the mystery of fast radio bursts, some of which originate near galactic centers. Could these be natural phenomena or something more deliberate? Of course, the galactic center isn't without its hazards. Intense gamma-ray bursts, supernova shockwaves, and the tidal pull of the black hole itself would make survival a constant challenge. But if life has taken root here, it would represent a form of resilience we've yet to witness. Perhaps civilizations in this region are transient, rising and falling like waves in a stormy sea, their legacies written in the very energy signatures we're only beginning to detect. The search for such intelligences is already underway. Projects like SETI have occasionally pointed their arrays toward the galactic center, listening for patterns in the electromagnetic static. Meanwhile, telescopes like the Event Horizon Telescope, which captured the first image of a black hole, are peeling back the layers of this chaotic realm. Every new observation brings us closer to answering whether the heart of our galaxy is a graveyard or a cradle of civilizations far beyond our own. One thing's certain: if life exists here, it doesn't play by the rules we're used to. The galactic center is a reminder that the universe doesn't owe us familiarity. Sometimes the most alien answers are hiding in the places we least expect, right under our noses, in the blazing core of the Milky Way. Most planets cling to their stars like children to a parent, but rogue planets are the cosmic runaways, worlds flung into the abyss untethered from any sun. Picture a frozen nomad drifting through the void, its surface plunged into eternal night, temperatures barely above absolute zero. It sounds like a death sentence for life, but here's the twist. Beneath that icy shell, these wandering worlds might hide oceans kept liquid by the faint, persistent warmth of radioactive decay or tidal friction. In the darkness, far from any star, life could be thriving in ways we're only beginning to imagine. Take Jupiter-sized rogue planets, for example. Their massive cores could retain heat for billions of years, creating subsurface oceans dwarfing Earth. Microbial life might cling to hydrothermal vents, much like the extremophiles near volcanic cracks in our own ocean depths. But there's an even wilder possibility. Smaller, Earth-sized rogue planets with thicker ice shells could act as natural cryopods, preserving life in suspended animation. Imagine entire ecosystems lurking in slow motion, metabolizing at a glacial pace, sustained by chemical reactions we've yet to discover. Then there's panspermia, the idea that life could hitchhike between worlds on asteroids or comets. Rogue planets with no star to sterilize their surfaces with UV radiation might be ideal waste stations for microbial stowaways. A microbe ejected from a dying solar system could freeze onto a rogue planet's surface, only to thaw in a subsurface ocean millions of years later. It's a cosmic relay race, with life passing from one nomadic world to another across the galaxy. The numbers add to the intrigue. Astronomers estimate there could be billions of rogue planets in the Milky Way alone, far outnumbering star-bound worlds. Some might even have thin atmospheres of hydrogen, trapping geothermal heat like a blanket. Others could collide, exchanging material and maybe even biology in violent, creative encounters. The catch: detecting these wanderers is brutally hard. Without a star to backlight them, rogue planets are invisible to most telescopes. But upcoming missions like NASA's Nancy Grace Roman Space Telescope could change that, using microlensing to spot their faint gravitational fingerprints. If we find one with signs of an atmosphere or geothermal activity, it would rewrite the book on where life can exist. Rogue planets challenge everything we thought we knew about habitability. They prove life doesn't need a sun, just warmth, chemistry, and time. And if microbes are out there riding the galactic currents in the dark, it means the universe might be far more alive and far more restless than we ever dreamed. Ceres might not look like much at first glance, a tiny, crater-speckled world barely 900 kilometers across, drifting in the asteroid belt between Mars and Jupiter. But this dwarf planet has a secret. Peer into its Arcata crater and you'll find something that shouldn't be there: dazzling bright spots glowing like alien headlights against the dark, rocky surface. These mysterious patches, first spotted by NASA's Dawn spacecraft, aren't just quirks of geology. They're likely vast salt deposits left behind by briny water that erupted from deep below. Proof that even the smallest celestial bodies can hide oceans of liquid water, and with them the potential for life. What makes Ceres so fascinating isn't just the presence of water, it's how that water behaves. Unlike the frozen moons of Jupiter and Saturn, where oceans are squeezed between layers of ice, Ceres' reservoir might be a global brine layer, a slushy mix of water and salts kept liquid by antifreeze compounds like magnesium sulfate. Think of it as a cosmic sponge soaked through with liquid that occasionally seeps to the surface through cracks and cryovolcanoes, those bright spots in Arcata crater. They're the dried-up remnants of these eruptions, like salt flats left behind after a lake evaporates. But here's the kicker: this isn't ancient history. Some areas show signs of recent activity, suggesting Ceres' underground plumbing is still pumping. Now consider the implications. If briny water is oozing up from below, it means Ceres has or had a heat source. Radioactive decay in its rocky core could be providing just enough warmth to keep that subsurface layer liquid, creating pockets where extremophile microbes might thrive. On Earth, we've found bacteria in places just as hostile, buried under Antarctic ice, trapped in toxic salt lakes, even inside rocks deep underground. Ceres' salt-rich brine could offer a similar refuge, with chemistry so rich it might power basic metabolic reactions. No sunlight required, just chemistry, water, and time. Then there's the bigger picture. Ceres isn't alone. Dozens of other dwarf planets and large asteroids like Pluto and Europa's cousin Ganymede likely harbor their own hidden oceans. Together, they hint at a startling truth that liquid water, and with it the potential for life, isn't confined to planets or even moons. Even the rubble left over from the solar system's formation could be teeming with wet, habitable niches. The real question isn't just whether life could exist on Ceres, it's how we might find out. Future missions could land near those bright spots, drilling into the crust to sample the salts and hunt for organic molecules. Or perhaps a probe could orbit close enough to sniff out plumes of water vapor like those on Enceladus. Either way, Ceres stands as a reminder that in the search for alien life, size doesn't matter. Sometimes the smallest worlds hold the biggest surprises lurking right beneath the surface, in the quiet dark of the asteroid belt. If Europa is a frozen enigma, its neighbor Io is pure chaos, a world so volcanic it makes Earth's eruptions look like candle flames. Jupiter's innermost moon is a relentless inferno, with over 400 active volcanoes spewing rivers of molten rock and plumes of sulfur that soar hundreds of kilometers into space. The surface is a patchwork of lava lakes, towering mountains, and vast plains coated in neon yellow sulfur dioxide frost. It's the most geologically active place in the solar system, constantly reshaped by the gravitational tug of war between Jupiter and its sister moons. But here's the twist: even in this hellscape, life might find a way. Think about Earth's own extremophiles organisms thriving in boiling acid pools, deep-sea hydrothermal vents, or radioactive waste. Now imagine Io's equivalent, microbes huddled in lava tubes where temperatures are just stable enough to avoid instant vaporization. Or perhaps life clinging to volcanic fumaroles, feeding on sulfur compounds the way some Earth bacteria metabolize toxic minerals. The moon's violent geology could actually fuel biology, with chemical energy from eruptions replacing sunlight as the driver of metabolism. It's a long shot, but not impossible, especially if subsurface magma chambers create transient pockets of liquid water, a byproduct of volcanic heat meeting buried ice. Then there's the sulfur. Io's atmosphere is thick with it, creating a corrosive environment that would dissolve most earthly life. Yet some terrestrial extremophiles, like sulfolobus bacteria, thrive in sulfuric acid, using it to power their cellular processes. If similar organisms evolved on Io, they might paint the moon's surface in subtle biological stains, patches of color invisible to the naked eye but detectable by spectrometers. Future missions could scan lava flows for these biosignatures, hunting for patterns that don't quite match geological explanations. But the real intrigue lies in the contrast between Io and Europa. These two moons orbit the same planet, yet they're cosmic opposites, one a frozen ocean world, the other a fire-breathing wasteland. If life exists on both, it would prove biology's adaptability knows almost no limits. Io challenges our definition of habitable entirely, forcing us to ask, does life need water or just energy and chemistry? The answer might come from Io's most mysterious features, its mountains. Unlike Earth's ranges formed by tectonic collisions, Io's peaks are likely thrust upward by relentless compression, some towering over Everest. Between these jagged spires, underground aquifers of molten sulfur could act as mixing chambers, blending chemicals in ways that spark complex reactions. It's a stretch, but if life does lurk here, these subterranean labs might be its birthplace. For now, Io remains a tantalizing what if, a reminder that the universe's creativity outpaces our imagination. While Europa's icy shell hints at life in darkness, Io screams the opposite, that even in fire and fury, the right conditions might just ignite biology's spark. The lesson: never underestimate a world that refuses to play by the rules. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary. A burst of noise so powerful, so inexplicable, that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that single, fleeting signal, 72 seconds of intense narrowband radio waves emanating from the direction of Sagittarius, has haunted scientists ever since. What made it remarkable wasn't just its strength, it was the frequency. The WOW signal hit at exactly 1420 MHz, a quiet band of the spectrum where natural cosmic noise rarely ventures, but where an intelligent civilization might deliberately broadcast. It was as if the universe had shouted directly at us, then fell silent before we could answer. Decades later, we still don't know what caused it. Some argue it was a passing comet, its hydrogen cloud reflecting sunlight in just the right way to mimic an artificial signal. Others point to more exotic possibilities: a rogue satellite, a glitching quasar, or even a one-time beacon from a distant civilization. But here's what keeps astronomers up at night: the signal was never repeated. Despite countless follow-up searches using increasingly sensitive equipment, the WOW signal remains a tantalizing one-off, a cosmic flare that vanished as suddenly as it appeared. That hasn't stopped the hunt. Modern telescopes like the Allen Telescope Array and the Breakthrough Listen project have trained their ears on the same patch of sky, scanning for even the faintest echo. Their tools are light, years ahead of 1970s technology, capable of parsing background noise for patterns that might hint at intelligence. Meanwhile, new theories keep emerging. Could the signal have been a laser-powered communication, briefly outshining its star, or perhaps a natural process we've yet to discover, like a neutron star's magnetic field interacting with interstellar plasma in just the right way? The WOW signal's legacy isn't just about solving a mystery, it's about how we search for answers. It taught us the universe is full of surprises and that patience is key. Every silent night of observation inches us closer to understanding whether that famous burst was a fluke, a cosmic prank, or something far more profound. Until we know for sure, it stands as a reminder: sometimes the most important discoveries aren't the ones we explain, but the ones that keep us wondering. Tabby's star doesn't just flicker, it practically winks at us with cosmic mischief. Officially known as KIC 8462852, this unassuming star in the constellation Cygnus made headlines when astronomers noticed its bizarre behavior. Massive, irregular dips in brightness, sometimes as much as 22%, far too extreme to be caused by orbiting planets. The internet exploded with theories, the most tantalizing being that an advanced alien civilization had built a Dyson swarm, a colossal array of energy-harvesting megastructures encircling the star. For a moment, science fiction seemed to edge into reality, but let's rewind. The original observations came from NASA's Kepler Space Telescope, designed to hunt for exoplanets by detecting the subtle dimming of stars as planets pass in front of them. What Kepler found around Tabby's star wasn't the gentle, predictable dip of a planet. It was a chaotic, jagged pattern of light, as if something enormous and misshapen were drifting across the star's face. The data defied explanation, leaving astronomers scrambling. Could it be a swarm of comets, a shattered planet, or, as some dared to speculate, a technological artifact on a scale beyond human comprehension? The megastructure hypothesis, while electrifying, was always a long shot. Enter Occam's razor, the principle that the simplest explanation is usually the correct one. Further studies pointed to a more mundane culprit: dust, lots of it. Observations from the Spitzer and Swift telescopes revealed that the dimming affected infrared light more than ultraviolet, a telltale sign of fine-grained cosmic dust blocking the star's glow. The irregular dips, likely clumps of this debris, perhaps from a catastrophic collision between asteroids or the lingering aftermath of a planetary-scale breakup. Yet even with dust in the mix, Tabby's star keeps throwing curveballs. The dimming isn't just deep, it's asymmetric, meaning whatever's blocking the light isn't evenly distributed. Some researchers suggest a massive, uneven ring system around an orbiting planet could be to blame, while others speculate about a highly eccentric comet family on a looping, destructive orbit. Then there's the star itself, unusually young, or perhaps recovering from a recent bout of stellar indigestion, belching out clouds of material that temporarily shroud its light. But here's why Tabby's star still captivates. It's a reminder of how much we don't know. Every time we think we've pinned down an answer, the data shifts, teasing us with new possibilities. The megastructure theory might be on life support, but the door isn't entirely closed. After all, absence of evidence isn't evidence of absence. We've only been observing this star for a cosmic blink. Future telescopes like the James Webb could analyze the dust's composition in finer detail, hunting for anomalies that don't fit natural models. So while dust clouds might be the leading explanation today, Tabby's star endures as a beacon of cosmic curiosity. It challenges us to stay open to wonder, to balance skepticism with imagination, because sometimes the most thrilling discoveries aren't the ones we confirm. They're the ones that keep us questioning, pushing us to look deeper into the dark, just in case something extraordinary is looking back. Pulsar planets sound like something straight out of science fiction, rocky worlds orbiting the corpses of massive stars that died in violent supernova explosions. These aren't just any dead stars, though. Pulsars are the rapidly spinning, ultra-dense remnants of those explosions, firing off beams of radiation so precise they sweep across the cosmos like interstellar lighthouses. The idea that planets could survive such catastrophic births, let alone harbor life, seems impossible at first glance. And yet, in 1992, astronomers made a jaw-dropping discovery. The first confirmed exoplanets weren't found around a sun-like star, but circling a pulsar named PSRB 1257+12. Picture the environment these worlds endure. Pulsars emit torrents of X-rays and gamma rays, enough to strip atmospheres and sterilize surfaces in seconds. Any planet locked in orbit would be bombarded by deadly radiation while simultaneously being stretched and compressed by tidal forces. But here's where it gets fascinating. Some of these planets might have once been gas giants, their outer layers blasted away by the supernova, leaving behind diamond-rich cores forged under unimaginable pressure. Others could be second-generation worlds forming from the debris of the stellar explosion, birthed from the ashes of their predecessors' destruction. Now consider the possibility of life. On Earth, we've found bacteria thriving inside nuclear reactors, feasting on radiation as if it were sunlight. Could similar extremophiles exist on a pulsar planet, evolving to use high energy rays the way plants use photosynthesis? It's not entirely far-fetched. Theoretical models suggest that if a pulsar planet had a thick enough ice or rock shield, subsurface oceans might persist, protected from the worst of the radiation. Life there could rely on chemosynthesis, drawing energy from radioactive decay or geothermal vents, much like deep-sea organisms near hydrothermal vents on Earth. Then there's the darker, more speculative angle. What if these worlds weren't always lifeless? Pulsars are the remnants of massive stars that once had their own planetary systems. If a civilization had developed around such a star, could they have seen the supernova coming and built underground shelters or orbital habitats to ride out the apocalypse? The remnants of such a society might still exist, clinging to survival in shielded caverns or buried beneath miles of rock, their technology adapted to harness the pulsar's relentless energy output. The challenges to finding out are immense. Pulsar planets are incredibly rare, and their harsh environments make them difficult to study. But the mere fact they exist forces us to expand our definition of habitable. If life can emerge in the aftermath of a stellar catastrophe, it suggests biology is even more tenacious and the universe more creative than we ever imagined. Pulsar planets may be cosmic ghost towns, the ruins of a system that once was. Or just maybe they're proof that life doesn't need a gentle star to thrive, just a way to endure. Either way, these eerie worlds remind us that the universe never runs out of surprises. Pluto, once dismissed as a frozen relic at the edge of the solar system, has turned out to be anything but dead. Beneath its thin, hazy atmosphere lies a landscape of staggering complexity, where towering ice mountains meet sprawling glaciers of frozen nitrogen. But the real surprise, the heart-shaped Tombaugh Regio, a massive plain of nitrogen ice that beats with geological activity, and at its edges something even more intriguing, dark, sprawling lakes of methane, their surfaces so still they might as well be mirrors reflecting the void above. This isn't the Pluto we imagined. the New Horizons spacecraft revealed a world where nitrogen geysers erupt in slow motion, spewing icy particles into a sky so cold the very air freezes and falls like snow. Those methane lakes, they're not just puddles, they're evidence of a hidden, slushy subsurface layer where temperatures and pressures might allow liquid or semi-liquid hydrocarbons to ooze and flow. Cryovolcanoes like Wright Mons rise kilometers above the surface, their slopes likely formed by eruptions of water ice slush rather than molten rock. It's a world where chemistry happens at a glacial pace, where reactions that would take seconds on Earth unfold over centuries. So how does this tie into the search for life? On Earth, methane is a classic biosignature, a gas often belched out by microbes in swamps and cow guts. But Pluto's methane isn't proof of biology, at least not yet. Instead, it's a puzzle piece in a much larger mystery. The interplay between methane, nitrogen, and water ice suggests a dynamic underground system where seasonal changes and geothermal heat could create fleeting pockets of liquid. And where there's liquid, even if it's a sluggish mix of hydrocarbons, there's the potential for chemistry complex enough to nudge toward biology. Think about Titan, Saturn's methane-rich moon. There, scientists speculate about life forms that use liquid methane the way we use water, with cell membranes built from nitrogen-rich compounds. Could Pluto's lakes host something similar? Not life as we know it, but life as we don't. It's a stretch, but not impossible. The slow dance of molecules in Pluto's extreme cold might follow rules we've barely begun to decipher. Then there's the question of energy. Without sunlight, any theoretical Pluto organisms would need another source, perhaps radioactive decay in the dwarf planet's rocky core, or chemical reactions between water ice and ammonia deep underground. It's a long shot, but so were deep sea vents on Earth until we found them teeming with life. Pluto's lesson is clear. Even in the darkest, coldest corners of the solar system, complexity thrives. Its methane lakes aren't just quirks of geology, they're windows into a world where the line between habitability and hostility blurs. And as we study more distant icy worlds, Pluto stands as a reminder. Sometimes the most alien environments are the ones that surprise us most. Oumuamua streaked through our solar system in 2017 like a cosmic whisper, here one moment, gone the next. This bizarre, cigar-shaped object was the first confirmed visitor from another star system, and it left astronomers scratching their heads. Not just because of its strange shape, but because of how it moved. As it raced away from the sun, something utterly unexpected happened. It sped up, not like a typical comet warmed by sunlight and shedding gas, but with a nudge that defied easy explanation. The leading theory, outgassing. When comets heat up, they release jets of gas that act like natural thrusters, giving them a slight push. But Oumuamua showed no visible coma, the fuzzy halo of gas and dust that usually surrounds active comets. No tail, no debris, nothing. That left scientists scrambling. If it wasn't outgassing, what was propelling it? Some researchers suggested exotic ices like hydrogen or nitrogen, sublimating in ways we couldn't detect. Others proposed more radical ideas like solar radiation pressure acting on an ultra-thin, lightweight object, a cosmic sail drifting between the stars. Then came the controversy. Harvard astronomer Avi Loeb floated a provocative possibility. What if Oumuamua wasn't natural at all? Its acceleration, its unusual shape, its puzzling lack of outgassing. Could these be signs of alien technology? Maybe an ancient probe long dead, tumbling through space, or even a fragment of a larger structure, broken free from some distant civilization. The scientific pushback was fierce, but the debate itself was valuable. It forced us to question assumptions and sharpen our tools for the next visitor, and there will be more. Since Oumuamua, we've spotted other interstellar objects like Borisov, a far more comet-like traveler. The difference is now we're ready. Projects like the Vera C, Rubin Observatory, set to scan the entire southern sky every few nights, will catch these interlopers earlier, giving us time to study them before they vanish. Even more exciting, missions like the European Space Agency's Comet Interceptor, designed to lurk in space, waiting for the next Oumuamua to whiz by, then chase it down. Imagine a probe rendezvousing with an interstellar object, analyzing its composition in real time. We might finally learn what Oumuamua was made of, whether it was a shard of exotic ice, a rogue asteroid, or something even stranger. Every new visitor is a message in a bottle from the cosmic ocean, carrying secrets from realms we can't yet reach, and the next one might not just be a rock. It could be the clue that changes everything. Imagine a planet where the oceans never end, no continents, no islands, just an endless expanse of water stretching from pole to pole, buried under a crushing blanket of hydrogen gas. This isn't science fiction, it's the bizarre reality of hycean worlds, a new class of exoplanets that could rewrite the rules of habitability. These aren't just water-rich planets, they're entire ocean globes with atmospheres so thick and dense they trap heat like a cosmic pressure cooker, keeping their surfaces liquid even far from their stars. And the strangest part, life here wouldn't need land to thrive. It might not even need oxygen. Let's break down what makes these worlds so special. Hycean planets are thought to be up to 2.5 times the size of Earth, with temperatures soaring under their hydrogen shrouds. Unlike our familiar blue marble, where oceans are cupped between continents, these places could have water layers hundreds of kilometers deep, pressurized to extremes where liquid behaves in ways we've never seen. Near the surface, the heat and pressure might create a supercritical fluid, a state where water isn't quite liquid or gas, but something in between, capable of dissolving minerals and organic molecules with terrifying efficiency. Dive deeper, and the pressure could forge exotic ices hotter than lava, their molecules packed so tightly they form crystalline structures unknown on Earth. But here's the real kicker. In this alien ballet of chemistry, life might find a way. On Earth, we've discovered microbes thriving in the most inhospitable places inside nuclear reactors, in boiling acid pools, even buried under kilometers of ice. Hycean worlds could harbor similar extremophiles, their biology twisted to exploit the hydrogen-rich environment. Instead of breathing oxygen, they might metabolize sulfur or methane, their cells armored against crushing pressure by molecular structures we can barely imagine. Some scientists speculate that the upper layers of these global oceans could host floating microbial mats, vast living rafts drifting on currents stirred by tempestuous winds in the hydrogen sky. The key to unlocking this mystery lies in the atmospheres. Hydrogen, while deadly to humans, is oddly transparent in certain infrared wavelengths, a quirk that lets telescopes like the James Webb Space Telescope peer straight through to the chemistry below. JWST instruments are finely tuned to sniff out gases like dimethyl sulfide, a compound that, on Earth, is almost exclusively belched out by marine phytoplankton. Finding it in the air of a Hycean world would be like catching the scent of an alien ocean breeze. Other biosignatures, like methane mixed with carbon dioxide but lacking carbon monoxide, could hint at biological activity reshuffling the planet's chemistry. Of course, not every Hycean world will be a paradise. Some might be trapped in a runaway greenhouse state, their oceans boiling into steam under too thick atmospheres. Others could be tidally locked, with one side eternally scorched and the other frozen, leaving only a sliver of twilight where life could cling. But the sheer variety of these planets is what excites astronomers. Unlike Earth clones, which need to check a dozen boxes to be habitable, Hycean worlds expand the playing field, showing us that life might flourish in places we once dismissed as hellish. The hunt is already on. JWST has begun analyzing suspected Hycean candidates like K218b, a mini-Neptune with tantalizing hints of water vapor and organic molecules in its atmosphere. Every new spectrum, every flicker of light captured, brings us closer to answering whether these global oceans are sterile or silently humming with biology. Hycean worlds challenge us to think bigger, to imagine life not as a rarity, but as a shape-shifter, adapting to whatever the universe throws its way. And if we do find proof of life beneath those hydrogen skies, it won't just redefine habitable zones. It'll prove the cosmos is far more inventive than we ever dreamed. The Orion Nebula isn't just a pretty cosmic cloud, it's a bustling factory of worlds, where the raw ingredients of planets and life itself swirl in a luminous dance of gas and dust. Located just 1,500 light-years away, this stellar nursery is so close and so bright you can spot it with the naked eye on a clear night, a smudge of light in Orion's sword. But peer deeper and the real magic unfolds. Here, newborn stars blaze to life, their intense radiation sculpting the surrounding nebula into pillars and cavities, while gravity works its slow alchemy, clumping dust and gas into protoplanetary disks, the birthplaces of future solar systems. What makes Orion so special isn't just its beauty, it's the chemistry happening in those disks. Telescopes like Hubble and the Atacama Large Millimeter Array have detected complex organic molecules floating in these clouds, from methanol to acetone, even simple sugars. These aren't just random chemicals, they're the precursors to life's building blocks, the same compounds that, on Earth, eventually link together to form amino acids and nucleic acids. It's as if the universe is prepping a cosmic buffet, scattering the ingredients for biology across fledgling planets before they've even finished forming. Now, imagine a young planet coalescing in one of these disks, bathed in ultraviolet light from nearby massive stars. That radiation should be deadly, breaking apart delicate molecules. But here's the twist: it might actually help. Laboratory experiments show that UV light can trigger reactions in icy dust grains, forging even more complex organics. The nebula's harsh environment could be a crucible, not a coffin, for life's ingredients. Over millions of years, these molecules might hitch rides on comets or asteroids, delivering their precious cargo to the surfaces of young worlds like cosmic Uber Eats. The implications are staggering. Orion's protoplanetary disks suggest that the universe doesn't just make planets, it might precede them with the tools for life. And this isn't unique to Orion. Similar organic-laden disks have been found in other nebulae, hinting that this process could be universal. Everywhere stars are born, the raw materials for biology might be spinning into place, waiting for the right conditions to spark something alive. But the real question isn't just what's there, it's what happens next. As these disks evolve, some will birth gas giants, others rocky worlds like Earth. A lucky few might end up in the Goldilocks zone, where temperatures allow liquid water to pool. And if those worlds inherited Orion's organic bounty, they'd start their existence with a head start, a sprinkle of cosmic potential baked into their very foundations. That's why astronomers are so obsessed with this nebula. It's not just a snapshot of star formation, it's a window into how life might get its start across the galaxy. Future telescopes like the James Webb will probe these disks in even greater detail, hunting for amino acids or other biomarkers. If they find them, it would mean the universe doesn't just allow life, it actively sets the table for it. Orion isn't just a spectacle, it's a clue whispering that we might be part of something far grander, a symphony of chemistry and chance playing out in the dark. We've spent centuries searching for life in the cosmos, but what if we've been looking in the wrong places, or worse, looking for the wrong thing? Enter the most elusive frontier of all, dark matter. This invisible substance, which outweighs normal matter 5 to 1, doesn't interact with light, doesn't clump into planets or stars, and slips through our bodies like ghosts. Yet some physicists dare to ask, could it harbor life? Not life as we know it, but something unimaginably alien, built from particles that dance to rules we're only beginning to guess. The idea sounds like pure science fiction until you dig into the math. dark matter's existence is inferred from its gravitational pull, but its true nature remains one of physics' greatest mysteries. Most theories assume it's made of weakly interacting massive particles, or WIMP, that barely notice ordinary matter exists, but fringe hypotheses suggest certain dark matter types might interact with themselves, forming complex structures through unknown forces. Picture a shadow ecosystem, dark atoms bonding into dark molecules, swirling in halos around galaxies, invisible to our telescopes but buzzing with activity. Here's where it gets wild. If dark matter particles can exchange energy through some hidden version of electromagnetism, they might form self-replicating patterns, a kind of dark chemistry. Theoretical physicist Lisa Randall has floated the possibility of dark stars powered by dark matter annihilation, while others speculate about entire dark biospheres where information is processed not by DNA but by arrangements of exotic particles. Life here wouldn't need water or sunlight. It might feed on the decay of dark matter itself, thriving in the voids between stars where normal matter is sparse. Of course, the hurdles are staggering. Without electromagnetic interactions, how would such organisms sense their environment? How would evolution work without radiation or predation? Some models propose that gravity alone could shape selection, with dense clusters of dark matter acting as metabolic hubs. Others imagine dark life as more akin to vast, diffuse intelligences, thinking in slow motion over cosmic timescales. The truth is, we're groping in the dark, literally. Our tools are built to detect photons and atoms, leaving us blind to 85% of the universe's matter. Even if dark life exists, we might lack the language to recognize it, but that's what makes the hunt thrilling. Every experiment hunting for dark matter, from underground detectors to space-based observatories, is potentially probing a shadow biosphere. A single anomalous signal could rewrite not just physics but biology. So while the idea remains speculative, it's a reminder of how little we truly know. Life might not just be stranger than we imagine. It might be stranger than we can imagine, thriving in dimensions or forms we've yet to conceive. Dark matter life forces us to confront the hubris of assuming we've guessed all the rules. After all, if the universe teaches us anything, it's that wherever there's complexity and energy, life finds a way. Even in the dark, some stars don't just flicker, they vanish. Not in supernova explosions, but in gradual, unnatural dimming, as if something vast and unseen were slowly wrapping around them, stealing their light. These bizarre stellar anomalies have a name among astronomers: Dyson Sphere candidates. The idea traces back to physicist Freeman Dyson, who theorized in 1960 that an advanced civilization might eventually harness all the energy of its host star by building a gargantuan swarm of energy-collecting structures, a concept now etched into science fiction as the Dyson Sphere. But here's where reality outpaces imagination. Telescopes like NASA WISE and the European Space Agency's Gaia have already flagged stars with infrared signatures that don't match any known cosmic phenomenon. Their visible light dims, as if obscured by something, while their infrared glow spikes exactly what you'd expect if massive solar panels or heat-emitting megastructures were soaking up a star's energy and radiating the waste heat. Take KIC 8462852, better known as Tabby's star. Its erratic dimming sparked wild speculation about alien megastructures before dust clouds emerged as the more plausible culprit. But other candidates like EPIC 2463934474 defy easy explanation. This distant star dims by up to 65% at irregular intervals, with no clear orbital pattern to blame. Then there's VVVWIT07, a colossal star in the Milky Way's bulge that faded by 97% over several years before brightening again. Natural explanations exist: swarms of comets, rogue planets with rings, or interstellar debris, but each stretches known astrophysics to its limits. What if these aren't cosmic coincidences, but glimpses of civilizations operating on scales we can barely fathom? The engineering challenges of building a Dyson Sphere are as staggering as the concept itself. Imagine dismantling entire planets to forge a constellation of mirrors, solar collectors, and habitats, all orbiting in precise formation. A full sphere would require more material than exists in our solar system, but a swarm, a loose network of smaller structures, could achieve the same goal incrementally. The energy payoff would be unimaginable, a star's entire output harnessed for computation, propulsion, or even art. That's the heart of the Fermi Paradox. If such civilizations exist, why haven't we seen them? Perhaps because they've retreated into Dyson swarms, their waste heat blending into the infrared background of the universe, invisible to all but the most determined searchers. Yet the implications cut deeper. A single Dyson Sphere candidate could rewrite our place in the cosmos. Confirmation wouldn't just mean we're not alone. It would mean intelligence can reshape stars, bending physics to its will. And if that's possible, then the universe might be far older, stranger, and more crowded than we ever dared to dream. Until then, these dimming stars remain cosmic riddles, whispering that the line between natural and artificial may be thinner than we think. After exploring 24 cosmic wonders, each a potential haven for life beyond Earth, we arrive at one final, unsettling possibility. What if the universe is teeming with intelligent civilizations, but they've chosen to leave us alone? This is the zoo hypothesis, a thought experiment that flips the Fermi paradox on its head. Instead of asking why we haven't found aliens, it suggests they might be deliberately avoiding us, observing humanity like rare specimens in a galactic wildlife preserve. Imagine a universe where advanced civilizations exist just beyond our perception, their technology so refined they can cloak their presence entirely. They might view Earth as a fragile ecosystem of emerging intelligence, one best left undisturbed to evolve naturally. The same way we protect uncontacted tribes in the Amazon or establish marine reserves to safeguard ocean life, these hypothetical neighbors could see interference as ethically fraught or even dangerous. After all, history shows what happens when advanced societies collide with less technologically developed ones. The results are rarely peaceful. This isn't just speculation. The zoo hypothesis draws eerie parallels to real-world conservation ethics. On Earth, scientists use non-invasive observation to study animals without disrupting their behavior, tracking wolves with drones, for example, or observing deep-sea creatures with silent submersibles. Apply that logic to a cosmic scale, and suddenly, the silence of the universe takes on new meaning. Radio signals, probes, even Dyson swarms might be deliberately muted or redirected to avoid contaminating our development. But here's the twist: the 24 wonders we've explored could be part of this grand experiment. Europa's hidden ocean, Enceladus's geysers, even Tabby's stars dimming. What if these aren't just natural phenomena, but subtle tests? Advanced civilizations might seed the galaxy with habitable worlds, then monitor which ones develop intelligence, treating the cosmos as a vast laboratory to study the emergence of life. The very anomalies that baffle us could be breadcrumbs left behind, clues placed just beyond our understanding to see if and when we're ready to spot them. Critics argue the zoo hypothesis is unfalsifiable, a cosmic shrug to explain away our loneliness, yet it raises profound questions about maturity and contact. If alien civilizations are out there, their silence might not be indifference, it could be restraint. The same way parents let a child struggle to tie their shoes, these observers might believe true growth comes from overcoming challenges independently. Until humanity reaches a technological or ethical threshold, perhaps mastering sustainable energy, abandoning warfare, or detecting cloaked probes, we remain in the galactic nursery, unseen but not forgotten. So as we look up at those 25 cosmic wonders, consider this: the emptiness we perceive might not be emptiness at all. It could be a curtain drawn just enough to let us stumble, learn, and grow, until the day we prove we're ready to join the conversation. The universe isn't silent, it's waiting. From the frozen depths of Europa's hidden ocean to the methane-soaked valleys of Titan and the tightly packed Earth like worlds of TRAPPIST-1, our journey through cosmic possibilities has revealed something extraordinary. Life, if it exists beyond Earth, could thrive in forms and places we're only beginning to imagine. These aren't just random dots in the sky, they're testaments to the universe's boundless creativity. Europa, with its salty subsurface sea, could harbor entire ecosystems cut off from sunlight, surviving on chemical energy alone. TRAPPIST-1 trio of Goldilocks planets challenges our definition of habitable, proving that even under the flare-prone glare of a red dwarf, stability might still carve out niches for biology. And Titan, a world where life might not even need water, rewriting the rules of biochemistry before our eyes. But what ties these discoveries together isn't just the science, it's the enduring human hunger to know we're not alone. For centuries, we've looked up and wondered, filling the silence with stories, speculation, and now spacecraft and telescopes. Every mission, every observation peels back another layer of the cosmic onion, revealing not just answers but deeper questions. Could Europa's plumes carry microbial hitchhickers? Does TRAPPIST-1 compact system foster panspermia, with life hopping between its worlds? Is Titan's methane drizzle nurturing reactions we've yet to fathom? The beauty is in the uncertainty, the tantalizing maybe that keeps us searching. So where does that leave us? Not at an ending, but at a threshold. The universe doesn't owe us familiarity, and that's what makes this quest so thrilling. Whether life is out there or not, the mere possibility expands what it means to be human, to gaze into the abyss and dare to imagine it gazing back. Maybe we'll find microbes in Enceladus's geysers or cryptic signals from a Dyson swarm. Or maybe the greatest discovery will be realizing how much more there is to learn. Now it's your turn. Which of these cosmic wonders sparks your imagination the most? The icy mysteries of Europa, the hazy chemistry of Titan, or the star-hopping potential of TRAPPIST-1? Drop your pick in the comments or shout out a world we missed. After all, the universe is vast and the conversation's just getting started. Stay curious. The next great discovery might be hiding in plain sight, waiting for someone like you to spot.